My name is Max. Welcome everybody. It's really an honor to have you here. I founded the initiative roughly 8 months ago with a couple of friends, where we started working in Africa, and now actually brought it quite far, this whole project. And today we're presenting you a couple of things. First of all, we start with a high-level introduction to what we're doing and giving you a context. Then we go a bit into more detail in the data workflow of the model, how we create data for the world, and what kind of role does governance and also contribution play, and how we can make it possible in such projects. Yeah, and now jumping to the context. In sub-Saharan Africa, actually, so everything below the Sahara, every second person has no access to electricity. And that's not just an African problem, that's a problem that 800 million people face globally in 2021. And it's not tremendously decreasing because there's a lot of population growth in this area. So the solution to that problem, as you could imagine, is just to connect people, give them electricity, be it a home solution, a mini grid solution, or even connect people to the main grid. In this context, there's also another thing which we need to keep in mind, that humanity is hungry for energy. We have for the last 35 years linear growth almost of the global average electricity consumption per capita. So there's no way that we will stop immediately with consuming less energy. And just as a side note, Iceland has per capita consumption of electricity of about 20,000. So it's a really regional thing, and that average is much higher for Western countries than the one you see here. So there's something we need to do, is we need to plan. We need to plan to connect people to the grid and to satisfy people like the energy needs of the future. And the thing is, if we do that poorly, if we're not planning properly, we have an unreliable energy system, which might lead to outages. Expensive energy systems, which is, for example, just taking money away which you could spend otherwise, or leading to an unsustainable energy system, which I think the Western world contributed a lot over the last decades. But that's turning, right? We need to go green. So good planning requires, first of all, good people. People make decisions, and they decide on all the points which I just mentioned before, like affordability, sustainability, and so on. But the energy system is way too complex just to decide feeling-wise, and that's where we need also good tools, and these are like kind of decision support machines. People understand them and use them. But why I marked understand this, right, is nowadays for energy system modeling tools which help planning, you either have at the moment like a black box where you cannot even look into what's going on behind the scenes, or an opaque box where you, for example, where they deliver you documentation, and that can be even sometimes worse, because now you see the equations and you're wasting time, but you don't understand anything because you cannot actually see what's there in the code. So that can be negative efficiently, from an efficient perspective, human efficiency. And then we have the third point. It's about transparency. So we need good transparency, and you can see that as a decision validator. It really helps to understand why people decided to go for certain direction based on the tools they used. And that can be open source, can be open data, or even reproducible reports. So just imagine you can look at a governmental report, national report, and can just reproduce the results, how they came to the solutions. And that's possible today, and something transparency allows, and that empowers people on one hand, but also tools which people then adjust. Yeah, so you can see now what other things are coming up on the tools list, on this arrow towards the tools. People can now participate in these tool groups. Can better get involved. Yeah, they can improve tools. They can just add some features if they want, or they can even lead certain directions of the tool development. And that's just what was possible with this transparency part. Yeah, and then in this sense, what we are doing is we're building an open digital twin of the energy system. And yeah, we're taking a lot of data to have the current situation right now, like at this year, or let's say the energy system from the last year. And once we have that picture of what's going on now, we can then look in the future more realistically and assume different scenarios. And we are building an African model and are heavily based on European developments, such as the PyPSA Euro and PyPSA Euro sector, Atlight, and so on. And that really helps. I think that shows already what power open source has, because we can just retake developments and further improve them and adjust them to another part of the world. Going to the next part, we need to actually differentiate what our initiative is not about, what it maybe can be about in future, and it gives you also a feeling what is involved in the energy system model. So on one hand, you have a solver that solves a certain equation. That's not what we're doing. Then you have a problem formulator. That's, for example, PyPSA. It has a lot of different setups which are designed to represent energy system, and these little puzzle pieces you can put them together to create like a model which you can then optimize and solve. What we are mainly doing, like PyPSA Euro and PyPSA Euro sector, the sector copy version, is that we create data workflow. So the data which is coming in the model, we're putting in the right streams so that the problem can be formulated and solved. And this is really PyPSA-Africa about. And what is also one of the new features where not many people are working on is the part on data creation. And we will hear later a bit more about that. But I'm really excited about that topic, because that really helps the whole community doing proper studies. Just not to missing it out, once you really want to apply that in industry, that tool, or use it for some certain governmental studies, maybe you also want to have a good user experience where I would say all kind of modeling tools should work or are working, making things more easier, yeah. And there's also PyM, which is great for visualization in that part. And then there's also the user interface. I think Timoa has some developments ongoing, but you know, that helps more people to access tools. But on the other hand, can actually also slow down, I would say, the development of, yeah, let's say the data workflow and data creation. But that's not part of like in our focus, but can be in the future. Yeah, now after giving you the context, just handing over to Davide.
I will go through what we are building, just for start, go more in details about how we are doing it. First of all, as introduced by Max, PyPSA-Africa wants to be an open energy digital twin for describing Africa, but built with Africa, because there are colleagues of us working right now from PyPSA-Africa from Africa. And our tool wants to serve policymakers, utilities, and any practitioner and researcher interested in this kind of analysis for Africa, or any regions, sub-regions of Africa. In fact, we want to have a tool for coordinated dispatch and investment across multiple countries and regions, which it's rarely available, and currently there is no such tool available. Our tool will also be based on existing open source data such as PyPSA Europe, PyPSA, and Atlight, which are the foundation that may improve the reliability and security of our results. To go more in detail, we want our tool to have special features dedicated both at the application and as well as focusing to the users. But starting from the application, energy investments need a lot of money, and therefore we need our tool to be able to perform investment optimization, coordinated with also dispatch optimization, to understand how the energy flows goes across different regions within Africa and outside also Africa. This resolution, since this type of studies are very regional dependent, the resources are not uniformly distributed. That's why we need to have an accurate modeling also at spatial resolution. And given the interest of the user and the application, we can have a very fine resolution at each country level, for example, South Africa, or by changing a simple string, we can analyze also the entire Africa in a very flexible way. Moreover, we want to have the spatial resolution, so which means the type of modeling that will be tailored specifically to the need. So we can also evaluate the tiny areas, for example, for a single country, or larger areas for Africa. Moreover, given the intrinsic multi-horizon period of energy studies, then our tool will have multi-horizon optimization and also sector-coupled analysis, and which are built upon the experience of PyPSA Europe in a similar way. In particular, our tool will also have special features oriented to the users. In fact, we want our tool to be easy both to learn and use. That's why it is coded in Python. And we want to have it accessible, transparent, and flexible to incorporate different features and data. This tool must be also customizable for different needs. And that's why, to complement all of this, our source code will be freely open, and it's published actually on GitHub, and it has a modular structure so that any of us can work together in the same code without compromising the others while working. And that's a very important skill. We do have a modular structure both in terms of functions. Let's say the entire problem is divided in different files, each one with a specific code. And within each file, we do have a inner modular structure with very easy functions so that it is also easy to work with. Our tool will support parallel co-editing because we want to be a large group, and so this structure will also help that. And the workflow, so to turn the configuration file and the data into the optimization model that we need is completely automated thanks to SnakeMake, a tool that is widely used in Python and also PyPSA. In particular, to show how we are building our tool, we can see that starting from the configuration files, and SnakeMake guides you from them to the solving of the model. In particular, we first download the data, then the data which are raw and there are a lot of holes and problems will be filtered, and then they are processed so that they can be easily digested by the network modeling. As introduced by Max, our main novelties are very related to the first part because in Africa, if any of us has worked in this field, data are very difficult to achieve, and that's why we need to combine different sources to reach our goal. In fact, the main tasks of downloading data, filter data, and populating data, we aim at transforming the open source data sets that are available worldwide, and many of them for the same characteristics, and we convert them to an accurate model description of the network, and as well as appropriate demand and renewable production by region. In fact, in our model, we need to have an accurate modeling of the network, which means substations and lines, as well as to know the demand and renewable production by substation. To do so, we need to understand what is the shape of, what is the regional extents providing demand and renewable production for each substation. And that's why we need to fill every region with data. And that's why you can see in the figure here that we need to fill every shape with information related to renewable sources, GDP, and population. And all this is going to be novel, and we will be published open source. In particular, one of the sources of the data is OpenStreetMap, and Lukas and Matin will talk more about this, because open source datasets about network are not so reliable depending on the region. And the artificial intelligence team will talk more about this and how to solve this issue. To further clarify the flexibility of our tool, in particular in terms of data workflow, we want and to give an overview of the content within it. So from the open source datasets to the final output, which are the network model and the data by region, we have SnakeMake that, given the options that the user has set, will detailed select the method and dataset that we use to reach our goal. And by doing this, we have a modular structure so that by easily changing a parameter, the automated workflow by SnakeMake can decide between a method or another one very easily. And any of you, if interested into, can contribute to develop their own method without compromising the entire structure of the system, which improves and strengthens the robustness of our approach. To give an overview of what is our current status in terms of workflow, here are shown the main blocks of our code where we are working right now. Each of these is basically a function that we are, a file with a lot of functions within that we are working on. I won't go in any details about them, don't worry. And just to have a good overview, we have half of these blocks which have a good development stage, and the rest is under development. But we aim at reaching a very good prototype by the end of this year. To contribute and to understand where we are working right now, we have 6 main work packages that describe what are our main needs. First of all, we need methodologies to understand what is the demand and to forecast the demand variations, to populate the shapes and give also a profile for the year about the demand and how it goes. That's why we are also interested in different methods about this. Similarly, we need to know the expected renewable energy production by each shape, and also understand what are the generators located in each substation. To do so, we need to merge different data sets to understand what is the most reliable configuration of the network. Moreover, we have to also understand where systems may be installed, so to make and infer good investment plans. And also, we are working obviously in merging all this data to provide a good network that can be used and solved by the optimization part. Lastly, we have specific work packages, the artificial intelligence recognition, that is working right now to populate data sets that are not available, because Africa, we know, has limited data, especially with respect to Europe. That's why PyPSA Europe has a lot of more data available than we have. And that's why our artificial intelligence team is working right now to understand what is the most up-to-date network configuration that may not be available on OpenStreetMap, and they will contribute to this. So I give the floor to Lukas. Please, the floor is yours. Thank you.
Yeah, hello everyone. Thank you, Davide. First of all, sorry for the technological hiccups. There were some changing circumstances which we had to adapt to. So I will make the start in talking about object detection and satellite images, and the thing will be rounded up by Matin. So hello everyone, my name is Lukas Franken, and let's get started. So when we talk about simulation, we always have to talk about data first, and what kind of data we can put into the model. Now, for this purpose, OpenStreetMap is really the go-to source for all types of geographic data. There's maps, roads, elevation, these types of things, but also power infrastructure, very useful to us. There's towers, distribution, transmission towers, substations, etc. So combining all of this, we put it into our model and can really make a good assessment of what a local energy system looks like. However, the reason we can use OpenStreetMap is that it has a very high level of quality. On the other hand side, this means that it can be cumbersome to put new data into OpenStreetMap, which causes basically this data set not to be complete. So here's a map of Africa, which you have seen previously as well. And it basically outlines the availability of precise energy infrastructure data. And we can see that in the north and in the south, it looks really solid, but there are some blank spaces towards the middle, especially if we compare this to a recent estimate of what the complete energy infrastructure of Africa looks like. On the right-hand side, this is really a beautiful paper by some people from Facebook and their collaborators. And what they basically did is that they inferred energy infrastructure from nighttime images of Africa, but their highest resolution was 500 meters for 1 pixel. So this is just enough to get a good estimate of what the total infrastructure looks like, but it's not really precise enough for our purposes. So we can't really use this for our models. And you can see that particularly in the center, in the Democratic Republic of Congo in the center, and some other countries as well, there are rather large discrepancies between the two data sets. So what we basically need to do is that we need to go very precisely over these areas and get a finer estimate of where the energy infrastructure is. Now, for this purpose, we are going to combine two technological advances that have made great strides over the last 2 decades. And the first one is satellite imagery. Many satellites rotating around the Earth, photographing every square meter there is. And on the other hand side, object detection, which has seen great developments over the last 10 years. And so, for instance, you can see some of these kites that the neural network is trying to recognize are really rather small, but the network is still able to recognize them. And we are going to leverage this capability to our advantage to infer where the energy infrastructure is. Now, in a way, this is an intuitive idea, and of course, we are not the first ones to come up with it. So there was a seminal work done in 2017 in a cooperation between the World Bank and Development Seed, which is a software company, and they were basically trying to apply this exact methodology to some areas in Africa and also Pakistan. And you can see, for instance, here, this is a before image. This was the data that they had of the local power structure. And you can see that there are many, it lacks a lot of detail, right? And there are some unconnected areas and so on. And they went over it with the neural network, and they actually managed to improve the available data substantially. And you can see the result here on the right. And at this point, this is a good point to mention that one of the developers of this project is also a project advisor for us, and we would like to thank him sincerely for his very helpful insights on what we should look out for in this project. Now, since this is such an intuitive idea, and since it has been done in the past, the question immediately arises, well, why have not people done it already for the entirety of the Africa, maybe even the globe? And the reason for this is, of course, money. It turns out to be rather costly to obtain solid satellite imagery. And there's little financial incentive to do it because there's very little commercial gain. So this immediately makes it more of an NGO task, more of an academic task. So it's perfect for the position that we are in. And so one might ask, well, why do we need so much satellite imagery in the first place? And the reason for this is twofold. So first, the neural network should be able to recognize towers from space. So for it to be able to do this, we first need to show it thousands of towers until it's sort of able to get the clue and sort of understand for itself what a tower looks like and where it is located in a picture. And then, of course, there's the actual task at hand where we want to infer the infrastructure. And for this, we, of course, need satellite imagery as well. So that's the detection task down here. And both of these really require a lot of money. And we have made a rough estimate of what this satellite imagery for the entirety of Africa looks like. And it turns out that our estimate is in the upper area of 5 digits, which is much more than a company with little financial incentive would ever like to spend on this, and a private person even less so. But as a share of a grant that of types of things that we are applying towards, this is sort of a reasonable amount of money. But we have gotten to work already, and you might ask, well, they haven't spent a dime yet. How can they have gotten to work already? And we have 2 main sources to basically develop prototypes and basically show to others and ourselves that we are capable of doing this. So the first data set is a data set by Duke, particularly on energy infrastructure from satellite imagery. And basically a team at the Duke University under the supervision of Dr. Kyle Bradbury has gone over all kinds of places all over the globe. So you can see Brazil, for instance, China, Mexico. They basically employed multiple people or a single person, and they went over these satellite images and made manually boxes around the energy infrastructure. And this then can be used as input to our models, and this can be used as training data. And this is publicly available, and we are working with that for one hand. And also at this point, another project advisor is Dr. Kyle Bradbury, the supervisor, and also big thanks to him. He has been really provided some very useful hints in our work. And then the second source comes from Mexa. Mexa is a company that basically sells satellite imagery, a very detailed one, very precise one. And usually they sell it, but whenever there's a catastrophe, they try to help and basically provide satellite imagery of the relevant areas before and after the event, such that crews on the ground are sort of helped and can sort of better assess where damage has been done and where help needs to go to. And one instance of such a catastrophe is obviously the COVID epidemic, the COVID pandemic. And as part of their effort in helping there, they have released satellite imagery of Ghana, Sierra Leone, and some other countries in Africa. And basically, since we don't have any commercial purposes in what we do, we can use this for our project as well. And this has been really useful. Now, in this data set, the towers are not annotated at all. So basically what we need to do is that we need to match the satellite imagery to data from OpenStreetMap that we have of the areas. And by matching the two, overlaying them basically, we can generate examples for our neural networks from this as well. Yes, and at this point, I'm going to hand it over to Matin, who's going to talk about the very interesting details of this work. And with that, yeah, I hand it over to you, Matin.
Yeah, thank you very much, Lukas. Yeah, that should be me. Yeah, my name is Matin, and I've been working with PyPSA-Africa for well over 6 months. And I'm an undergrad, studies AI and maths at the University of Edinburgh. I'm currently in my final year. My colleagues like to call me the outlier because I'm the only undergrad within the team of PhDs. But I quite enjoy it. So I will ask Lukas to move the slide forward so we can see a lovely picture of the underwater because we'll be going for a deep dive. So maybe if you'd like, you can put on your snorkels and make sure your oxygen tanks are full because we're going to be taking a look at how we exactly do the satellite imagery detection. And a lot of this part revolves around data because that's where we spend the majority of our time. And this involves cleaning the data, processing it, making sure it fits into our model. Here you can see the coverage provided by Maxar for one such country. This is Sierra Leone. On the right side, you also see a small strip of image, which one of these boxes is actually. And if you look closely within some of these boxes, the upper boxes, yeah, exactly, you can see the towers that are overlapping. And we would like to pretty much overlap these two things and get our data. But on the next slide, the problem seems to be one of big data, which is something that has plagued this project throughout. Some of these TIFF files for satellite imagery are very large for Sierra Leone, around 21 TIFF files, about 45 gigabytes. But for large countries like the DRC, you have about 690 TIFF files with about 1,000 gigabytes. So my poor little Ultrabook doesn't really handle those very well. And also the OSM data for complete Africa is about 100 gigabytes uncompressed and would take around, conventionally takes around 12 hours to extract all of this power data. However, we've created some in-house solutions such as the OSM power data extractor and the TIFF tiler. The power data extractor allows us to extract all of these transmission infrastructure for the whole of Africa within 20 minutes or so, operated using SnakeMake, which is a favorite amongst my colleagues. And we can also do basic cleaning operations such as filtering out HV lines and things like that. The TIFF tiler is also amazing because we give it some of these locations of towers and it finds the relevant satellite image file and saves all of those tiles as PNG files, which we can easily view and review, and also offsets the locations of these towers, which is particularly useful for machine learning tasks. So what do we have next? Yeah, so far we've got the extractor, and then we take all of those tower locations, we give it to the tiler, and we get some of these images you can see below. But you might be able to tell that in one such image you have clouds, the other one you've got a few black borders. So what I'll talk to you about now is how we filter out those images. And it's almost like the jellyfish, which clears out the water. Here, a set of cloudy images, very cloudy. Sometimes they're partially cloudy. On the next bit, you'll see some dark images, also could be cloudy, but they're very dark. And how we exactly do the filtering is we took 35 hand-picked good images, and we converted them to grayscale, and we plotted their histograms, and the x-axis on the histograms, they're binned by the pixel values. So as you can see, most of the mass of this histogram sort of lies between the pixel values of 75 and 100, if I remember that correctly. And for cloudy images, we take one cloudy image and we pass it through grayscale, plot a histogram of one such image, and we can see that a lot of the mass lies towards the brighter pixel values, around 250, 256. And there's a red line as well, which shows you the sort of threshold that we picked that will work well around 110. So if the majority, like let's say 50% of pixel values lie above this range, we consider the image as cloudy, and this has been working very well. Similar approach for dark images, grayscale, histogram, and this time around, most of the mass lies towards the lower end. So we pick out the images, the pixel values below 50 or so. So that's sort of how we get rid of these cloudy images and dark images. But there's also blurry images. These are removed using a technique called singular value decomposition. And then there's black borders as well, which were quite easy to pick as well. We just check each side. If there's a row of black borders, consider the image as a black border image, and we delete it. So now putting things together, extractor, tiler, filter, and now we get beautiful images with labels on them, and they're labeled as towers. So this brings us to the next part, because we need these images for doing our deep learning. This is sort of the rock bottom from our deep dive so far. We've been using Detectron 2, which is an object detection framework. It's quite nicely structured, made by Facebook. Everything is configurable and takes away a lot of the complexity of object detection. There's a model zoo available for Detectron 2, as you can see on the right, various models. You can just pick and choose and use whatever model you want. So adding Detectron 2 to our workflow, next slide. Oh, we got TensorBoard as well. So yeah, we've been using TensorBoard to sort of track the training of our models and visualizing these results. And it's quite nicely integrated with Detectron, works with all of those models. So that's what we've been using. And adding it to the general workflow, we sort of, I sort of just last night let it run for a bit and trying to get you some results. And we pre-trained it on a RetinaNet, which is sort of a transfer learning style, where we sort of train the top layers. And we use like the Google Colab standard GPU for about 2 hours, 4,000 iterations. The sort of results that we get on our test set are, which is around 200 images. We get an AP of 31.2, but that result should be taken with maybe a kilogram of salt, because I found out a little bug in our code, which means might not be as accurate. So here are some detection results as well. So, I mean, the thing works. We detect some towers in the images. They're not the best detections. If you can see, the bounding boxes are not perfect. And that brings us to some challenges as well within this project. And that is relative to the size of these images, the towers are very small, which makes it almost as hard part of a task as maybe cancer cell detections, right? And another problem is the lack of accurate bounding boxes we have for these. And we would have to maybe go through the whole data set and label those by hand. But for the small towers, what we can do is we can use a technique called super resolution, which is maybe CSI Miami style sort of enhancement of images, where features are hallucinated into the image in order to make it in order to increase the resolution. So here, this image on the left is increased almost by 4 times. So the image on the right, and but as you can see, they look very similar. The tower in the image looks quite similar. And yeah, this is based on the original super resolution GAN, published in 2017, and it works very well. Trained on the COCO data set, which is a popular data set for object detection. So yeah, moving on. This is sort of where our super resolution would fit in within the whole system, within the whole ecosystem of things. You would have to run all the images through the super resolution and maybe filter those out and do everything on this higher resolution set. We have so far not dipped our toes into this. We have not proven the success of any such super resolution technique, but there is plenty of literature, in particular one that says that super resolution is a very inexpensive task that brings about significant improvements in a model. So once we get our basic models working, we can also try out some of these techniques. Yeah, and I think I will probably end this on the note of a quote that says, "We can recognize everything from sky using satellites," but I would add a big asterisk to it, and that is, if the resolution is right, we could probably do that. Yeah, and I will also pass it over to Max to sort of wrap it up and give you a nice conclusion.
Okay, thank you, Matin. Yeah, like as you see, like we are pretty much at the limit of this talk, so we have 30 minutes left. We will actually stay a bit longer, so to give you a bit space for Q&As. We will rush now to through the next slides, and then give you some time to like for the Q&A. Yeah, in general, I just want to give you our vision. It's practically, we want to create a useful alternative to closed source energy system models that are useful for industry and research. Some kind of Plexus alternative, right? And what we want is to work together and get fundings together, 1, 2, 3 fundings, and work on the same code base, like avoiding code duplication as much as possible, and see contributions coming in. The next slide. In this context, governance can really help the community to coordinate in terms of contributions, projects, or surrounding activities. And there are different options. Mainly, like from the Apache Foundation, there's a version how to work together in this context. Or Linux Foundation has also a couple of thoughts on that. And these are the way forward. Like that's the way forward we think that projects has to develop to get more impact in future. So next slide. If you think about, okay, governance, that sounds like, okay, government, it sounds like a bit slow progress and all that stuff. And moving to the next slide, it's not really, like it doesn't really slow you down. You're still independent on what you want to develop or what you can develop, because you in GitHub or in GitHub, you're independent and you can develop fast because you have forks and branches. So whatever you want to do, you can do it. But if it comes to the code base later on, there's where we think, yeah, like the community should decide what goes in, what goes not in. Okay, next slide, almost the last slide. Okay, if you join, yeah, you cannot just run before you're not walking. And that's the same thing with open source projects. Like, first of all, you must understand what's going on. Then it's also good to use it. Next step is to participate. Then you can maybe contribute some features back and maybe lead. Jesus. Okay, I just lost my mic for a second. Can you hear me? Probably yes. Okay. Can you hear me?
Yes, absolutely.
Okay, cool. Yeah, and then maybe you can lead a project as well, be it a new method on the demand or whatsoever. In that context, what are kind of the big projects ahead? So at the moment, we have around 15 developers who work actively on this project. We have 5 outreach people doing things surrounding the code base, for example, supporting this event and so on. And then we have advisors who practically can lead a couple of funding opportunities or helping us in some technical aspects. Yeah, that's just some info on how to reach out. You can just go on our website or on our GitHub. We arranged some kind of buddy talk where you can just book with me every Friday for 20 minutes in a 1-hour slot, a meeting. So easy to reach out. And yeah, that's it. And now we would just open the floor for Q&A. And as I said, like, we stay a bit longer. If you have to leave early, yeah, please try to be quick with asking. We have 9 minutes before it's free. All right, are there any questions? So the one thing is, okay, if you have questions, can you open your mic as well? Is this possible? Ask all to unmute. That's probably not the way to go forward. Okay, I think we got a question for yeah, on the images. What's the GSD of these images? So the ground sampling distance. Lukas or Martin, can you answer
that? Sure. Yeah. I mean, to be completely honest, Matin, you can help me out here. So what we know about the picture and what is really relevant for training models is what the resolution is. And the resolution that we are always striving towards and that we have in the data sets that I talked about and we talked about is 0.5 meters for 1 pixel. And this is really where the models can, you know, leverage their their potential. If you get, I mean, so there's data out there for 10 centimeters per pixel, but this is not realistic to get on a large scale, so it's not really useful. And then there's the publicly available data globally, which is really coarse. The best you can get there is like 10 meters per pixel or something. So the resolution is really the relevant quantity, if I'm understanding the question correctly. And this is 0.5 meters per pixel.
Yeah, absolutely. I just tried like doing a quick Google search on this thing, but as it seems like we're already like sort of bootstrapped for these images. They're not the best images, right? They don't have these masks for the clouds and everything. We're doing our own little cloud detection. So a lot of these, I believe there's other coefficients that are usually available in satellite imagery that you purchase, but it's not available in this one. This is a very bare bones imagery which is put out for free and is actually quite difficult to sort of deal with and process. So but maybe I think that's why sort of that makes this task a little difficult as well. But we found that 0.5 meters per 0.5 meters per pixel seems to be sufficient to test out some sort of training, get some sort of results. But in the future, as you've seen, we've got some super resolution in the works as well, which should further increase this resolution. So although not the same way as a satellite would, but and I think that should help as well. So we're going for even greater resolution at this point.
I think
so yeah.
that's good. And we got another question, and Leon is also raising his hand, but I'm just answering quickly the question from Robbie. Like he asked about, okay, like most network information are sitting around in a CAD design file. Can we take them and check the integrity of the estimation methods? So like, I think that's a really important note here. All these AI techniques to detect assets, they are used as a method to quicker prove if things are wrong. So a human will need to check afterwards if there's a real tower or not. And we doing this, it's often called donkey work. We will do that in our community and check if these assets are correct and feed like the data. And yeah, if governments want to provide better data, that's always possible and welcome. But as we know, TSOs are sometimes really restrictive and like when it's going to data sharing and so on. Yeah, Donald asked about the underground cables. Yeah, they're indeed hard to detect from images. So you can't see them. Yeah, that would be, for example, commercial data really helpful. But just one note: even pipelines are detected from pictures. And if we can look at historical data where the ground is like maybe we can detect them somehow as well. Okay, Leon, I'm just giving you now the. Okay, Leon, I think you can already ask, right?
Yes, thank you very much, Max, and the whole team. Great presentation and good work. I really appreciate the whole open source approach. And basically, you also answered my question, because it was on why there's no cooperation with African TSOs who might have much more, data and information, which might help out a lot. But yeah, as you've mentioned, it's usually very restricted, and that's why you choose this approach. But yeah.
Absolutely, and maybe instead of saying please share your data for whatever, we give them now a tool where they actually can have a benefit from it, right? Let's say before they had no real benefit of maybe sharing the data directly, but now we can in high resolution, high spatial resolution, use this data and give them cool tools. And yeah, maybe something comes out of that in future.
Yeah, great. It definitely looks like a great project, and I'm looking forward to hear from you in future. Thank you.
Thank you, Leon. And Matthias?
Yeah, hi, this is Matthias from RMI. I just want to start by saying thanks, guys. This looks like some really awesome and cool work. So thank you for doing it. Could you just say maybe a few more words about your estimated development and release timeline, as in when do you expect people can actually start playing with this and doing some modeling on the PyPSA platform?
A good question. So we plan to publish a prototype until end of this year. So far, it looks really good that we're in time. Yeah, and then you can actually use it. Now you can already use some parts. OSM extractors, for example, ready. You can extract OpenStreetMap data actually all across the world. Yeah, Maybe that's also good to know for you guys here in this chat. We actually looking on going also beyond Africa. Like we won't stop there, creating similar initiatives to increase the developers in that scope. And like to answer your question directly, we have no perfect timeline for the future steps. Like after the prototype, you will definitely hear more about what's coming next and so on.
Okay, looking forward to that. Thanks.
Perfect. So we got a couple of other questions. Yeah, one is why we do not partner with other initiatives, for example, joining the EMP and EMPA activity. If it makes sense, if you want to bring us in contact with them, we would like to look into this. For now, we just created the prototype based on a European model, which has really cool like capabilities. And yeah, we really pushed now on the code side to get this prototype done. Then yeah, Michael from the IES Institute from Edinburgh. Thanks to the IES for also actually advertising our events. Michael, you ask about, can you differentiate between AC and DC lines? Yes, we can. Quote Obama. Okay, then Andre, are aware of Facebook initiatives like Facebook Free Open Source? Yeah, like we are aware of this Facebook work. They did some cool stuff. If you want to, yeah, perfect. You shared us a contact. We will look into this.
Sorry, I mean, the Facebook thing is exactly, this is what we compared the data that we have from OSM to. Basically, what the Facebook guys did is that at a very low resolution, they looked at what energy infrastructure exists in Africa and they got a rough outline. And actually, we look very precisely at the mismatch between the data from OSM and the data from Facebook. And we see, okay, there are areas where precise data is still needed. And this is exactly the data that we are striving towards. So yes, the Facebook project was awesome to basically line out where we need to apply our methods first. But yeah, their data was not exactly. So the highest resolution was 500 meters per pixel. So you can't really model anything with this, but it was good to point at the right directions.
Yeah, and I think this Facebook work, they created a network artificially with a cost function, which sometimes worked and sometimes not. So it's a real rough estimations and estimation in that sense. Yeah, then Heidi asked, will you be open for other model frameworks like OEMF, osmosis, times, and so on? Yes, if it makes sense, absolutely. Like we can link models. In general, I think we also provide data which makes the whole community happy. For example, detecting and creating the data sets for network structures. A couple of, yeah, I think PyPSA Europe and PyPSA EuroSec, they have some cool functions in that sense. So if another model does a bit less than our model, then maybe yeah, it doesn't make sense to yeah, basically build in something. But yes, like if others did something cool, we can integrate it. And one cool thing is about that we're not using GAMS, we're using Python. So you don't need a license for that, for Python, and it's kind of easier to read and write code for that. But yeah, in general, we are open to integrate whatever is good and missing. Okay, when would you be guys open to taking projects outside Africa? Are you guys looking for funding opportunities? We currently applying in total for like a couple of projects in the horizon. So we have, I think, around 10 million funds, which are probably coming into this PyPSA-Africa project with 2 projects, another 1 million fund with a Libri project if it's successful. And yeah, the question is, when we look outside Africa, we are already starting to look outside Africa. You can just give us a note, and maybe we can also collaborate on creating somewhere in your region. And yeah, absolutely. End of next year, we hopefully have also a kind of global expansion, because what we really focus on is on scalability. Many of these methods, this OpenStreetMap extractor tool, for example, that works already global. So there's a couple of features which work already globally. Okay, then another question from Pierre. When applied at scale, is the intent to do detection for the entire continent, or will you be a greedy approach to avoid certain patches of the continent to reduce imbalance of the problem? Lukas, you want to answer that, or Matin?
Sure. I mean, it really depends on the amount of money that is available. So, for example, for DRC, we have seen particularly large mismatches between what is in OSM and what is there on the ground. And I think we would sort of probably look at that satellite imagery first. And if funds are available, probably invest it in this region first and not, for instance, South Africa. But yeah, I would see it in relation to the total amount of available money what we have, and go in these regions first.
I would also add, maybe there would also be some sort of computational cost associated with it, because there's almost more than 1 billion tiles in Africa. If you tile them up, there should be about 1 billion tiles, and more than 1 billion, and at 0.5 meters per pixel. And we're not sure how computationally feasible that would be. And of course, adding in those costs as well on top of the ones for satellite imagery. So I think that's definitely a very good approach. One such technique would be to take a lot lower resolution imagery, like maybe at 10 meters per pixel, and sort of like guess where which patches are relevant, and for the relevant patches, zoom in and grab the higher resolution imagery and work with that. I think that's sort of one such idea we have in mind right now.
Then thanks, Matin, and thanks, Lukas. There's a note from Andrew. Facebook using very high resolution images and also images outside the visible spectrum, so like kind of heat signals, and yeah, to detect lines. Higher loads in the lines have higher temperature during the night. And yes, I think you just mentioned a really nice alternative to the way we approach the whole thing. And that's exactly one example where some research, like one person, one group can now grab this part which you said and detect assets with kind of heat signals, or like there's also a sentinel data on elevation data. So towers just go up in a flat ground, and then you can also detect towers in that sense from kind of elevation signals that you generate from satellites data. Yeah, please, if you want to open project, want to fund that project in that direction, that's something which is highly welcome. Maybe one note, we can also detect the technical configurations to a degree. So we can say, okay, this is maybe a 800 volts substation or a smaller substation. That's something we would just do by training our data set with 400 kV substations on really high resolution pictures. And as from Matin said before, we can detect really almost everything. There probably we need some kind of validation if the technical stuff is good. Like that's probably harder to get the validation right. But that's how we can speed up the process at least. Will Joy ask an amazing and dynamic use for satellite images, and I look forward to hearing how it progresses. Okay, it's a statement. Thanks, Will. All right. Any other questions? Okay, if not, we would just end the session now. Sorry about the technical problems. Yeah, things really were difficult today. We missed the first bit of the recording, so I think my introduction, we missed that. We will deliver that afterwards and publish all parts of that event on YouTube, so you can share it with your colleagues, friends, and so on. Please feel free to reach out, and yeah, thank you all for joining, and have a great day.